Okay, so good afternoon. We have today a research presentation seminar where three PhD candidates, Juan Ramirez, Vicente Ano, and Temecho Zeudi, will present their research results before their defense. So this is not a defense presentation. The defense is scheduled in middle of December. The purpose of this research presentation is to inform all the School of Engineering, what they are doing, what are their achievements so far, and to give a flavor about what the defense will be about. We'll have an agenda, and we'll start with every presenter, which we have roughly speaking 20 minutes and 10 minutes for the question and answers. Please ask your questions at the end. I think every presenter will be much comfortable. And in this moment, the floor is given to Juan, which will start his presentation. And his PhD advisor is Dr. Nian Zhang from Electrical Engineering Department. So, Juan, please go ahead.
Hello, good afternoon, good evening, I think. My name is Juan, and I'm going to be presenting on deep learning approaches for hyperspectral classification and time series prediction. My advisor, like Dr. Cortez said, is Dr. Zhang. She's not in the city right now, so she couldn't join us, but she sent her regards. Let me start by trying to give you an overview of the entire project, right? The idea comes that from deep learning approaches have had a great impact in a lot of different classification and prediction problems. They have applications that have solved problems in cybersecurity, natural language processing, and other fields, right? So we want to take that success and apply it to other fields that have not reached that level of expertise. Now, what field could that be, right? We focus on the data that comes from environmental data. That's data that's captured with sensors, measures either temperature, light, precipitation, wind velocity, things that have to do with nature. Now, in those data sets, they start increasing in size. We start getting massive amount of data sets. All this is very good for deep learning approaches. But the problem comes that with all this big amount of data, we end up with a little bit of noise, a little bit of systems that don't have completely linear systems. And we have to come up with new hybrid approaches to tackle these problems. These hybrid approaches are the ones that we're focusing on. The first approach is based on a context-based feature augmentation. In this approach, we want to tackle hyperspectral classification using CNNs, right? Convolutional neural networks. The second approach is to implement a kind of adaptive filter to deal with nonlinearities of a time series prediction. In this case, we focus on data sets related to stream flow. All our experimentations are done with real world data sets, so it's not synthetic data set, it's actual real data. And I coded everything in Python. Right? So that's just the huge overview, right? In a very few words. Now, to give you a little bit of a background, deep learning comes from machine learning. Machine learning is like a little umbrella, which is a sub part of AI. AI comes from 1935, let's say, long time ago. And since then, they've been trying to figure out how to make machines smart. So at this point, we are almost there, right? Machines have reached level of expertise in many, many fields. Cars that can drive themselves, planes that can fly themselves, right? Machines that can perform surgery, algorithms that can predict what stock market is going to be better next year, and among others. But all of these solutions are based on good quality and enough quantity of data. If we don't have good data, these algorithms will not produce good results. So when we look at environmental data, we are faced with that difficulty that the data is not entirely clean. The data is, we cannot really capture every aspect of the data. We cannot capture everything that impacts a specific data that we're looking at, a specific target variable that we're looking at. For example, when we try to measure flow, like a stream flow, we need to take into consideration temperature, precipitation, and even take into account weather prediction, like real-time weather prediction, right? And this data, we don't have it entirely. We don't have the subset that we have doesn't represent entirely how the population data set works. So we end up with a little bit of imbalanced classes. We end up with imbalanced data distributions. We end up with a little bit of noisy data samples. And we're facing these nonlinear systems. So in this case, right, deep learning comes around, and deep learning tries to tackle this problem. And in many cases, already have solved many problems. In the publications that we have, we already have read many. I read many papers, and they all have been using some kind of deep learning approach. They base it either on convolution or they base it on LSTM, recurrent neural networks. Right? So those are the solutions that have the best performance out there right now. So based on that success, we came up with this methodology that at the core of the learning algorithm, it is a deep learning approach. But we added a couple of steps for pre-processing the data so the algorithm is better at classifying and is better at predicting. What are these pre-processing? So if we take a look at the center of the slide, I have this little diagrams, one green one and one like blue one. The green one is the one for classification. It's a 4-step process. And the blue one is the one for prediction, also a 4-step process. The idea is we capture the data, we pre-process it, then we feed it to our learning algorithm, and then we produce the results to see how well they classify on one hand, and on the other one, how well they predict it. For hyperspectral classification, we added this context-based feature augmentation. The idea here is that by using this augmented data, we get better results. On the other hand, to deal with the nonlinearity of stream flow data, we added the scar filtering. The idea here is the scar filtering is going to emphasize changes in the data. I want to emphasize changes, not smooth the changes, but actually emphasize them. Based on our experiments, this actually improved the results of the prediction. Of course, we have to adapt it a little bit to the specific data set because when we were testing it just off the box, we couldn't just apply it. We had to adapt it. So here we have some of the equations that we use to make that little adaptation. The first equation is just a Gaussian white noise, right? Where R is a random number, then mu it's the average expectation value 0, and then the sigma corresponds to the noise variance. Why do we need this? We want to know. What we do is we get this value of variance from the entire data set to see how much it varies, right? Based on this variation, we design a level of noise that will not negatively affect the data. It will disturb it a little bit, but it will not negatively affect, and it will not negatively affect the performance of our classifier or the performance of our predictor.
Yeah, so Juan, Dr. Sasania has a question, so we like to allow the questions during the presentation. So
Sure.
Dr. Sasania, go ahead.
Yeah, I'm so sorry. The poster size is not readable. It's not readable. It's too small. The
So Juan,
equations,
can you increase
no
the slides?
PowerPoint, slides, no PowerPoint slides. These are
Not at this
posters.
moment. I can try to zoom
Posters.
in if that can help.
I even tried to increase my font here, but it's blurred. I couldn't read it.
Okay, I'll go back to the regular PowerPoint. I think I can zoom in there,
I
but
think
you will have to bear with me when I move the screen a little bit.
I think
May I, from my, that was Asana, from my side, I increased until 143 and I can do much more. So Juan, can you do the same issue from your side? There is,
No.
I did increase. I mean,
Let me
size.
let me try to focus a specific area. I cannot make it the whole thing bigger, but I can.
yeah,
let me
okay,
zoom in.
that is good.
Am I still sharing my screen?
Yes.
Okay, so now I think here I can make it bigger.
Oh yeah,
All right, so sorry. That's what I mean
yeah,
by
now
it.
it's good. No, lower. Okay, now, yeah, it's much better.
Okay, so here we have these equations that are the ones that we use to
Correct.
do the pre-processing part. How do we calculate the amount of noise that we want to add? And here is our scar filter mask that we apply to the data in order to accentuate the changes in the data set. Now, in order to evaluate how well our algorithm performed, we did different things. One of them is that we partition all the data into segments so we can run a cross validation on it. So here's this figure, the orange and blue figure, shows how we did that, right? So we divided into different chunks of data. We set apart a little percentage, like 10% for testing, 10% for validation, and we use about 80% for training. But we rotate them, right? So we don't use the same ones all the time. We start switching them around. So every time we run a different experiment, it will use a different set of data samples to test and to evaluate. So this was our tenfold cross validation. That's what we end up using in our experiments. Now, in addition to that, we use other things to evaluate. One second. So in order to check the performance of the classifier, we use what we call confusion matrix, right? This is just a little chart where we say whether we match a specific class or not. We also use the classification report. This consists of 4 columns: precision, recall, F1 scores, and support. These are based on the values captured in the confusion matrix. The most important one that we use to check if our results were good and to measure accuracy was the root mean square error. Here we have the equation. In this case, our y sub i's are the true values, the values that we're expecting to produce, and the y sub I hat, that's the one that we are predicting, right? So in this case, if we achieve perfect prediction, we should be getting a value of 0. So we created different kind of experiments. In this poster, I didn't put all the different pipelines that we established for all the different experimentations, but we did create different type of experiments, right? But we based everything on real data sets, and here are 2 of the data sets that we were using. The one on your right, the right-hand side is the one for stream flow and time series collection, right? So this comes from the Potomac River. This is a nice picture of the Potomac River. And this is the data that is captured by USGS, right? In one of the stations, they have multiple stations across all the country. This is one station, one point of data, one series of data. On the left-hand side, we have the hyperspectra cube collected. This is not near here. This is actually from the University of Pavia in Italy. So they take a picture for either an airplane or from a satellite. And this picture is not just a regular picture that we can see, right? The picture has more than just a couple of frames, right? So in this case, this is the picture on the y-x axis. That's the regular picture. On the z-axis, we have the spectra images. what do I refer to as spectral images? These are images that are captured by either infrared light or near infrared light, or even thermal, how hot it is, right? So all of those are added, and that becomes the cube, right, of data input. So on one hand, we have cube data, and the other one, we have this kind of stream data, right? This time series data. So here I'm going to show you some of the summary results that we have so far. On the left-hand side, confusion matrix, right, for 3 different type of deep learning models. We have the confusion matrix. The idea is you want to see values only on the main diagonal. Those are the good values. If you see anything that is off the main diagonal, it means that the classification or prediction has some problem. As you can see, the one that achieved the best results is the one in the middle, the one that corresponds to convolutional neural networks. Same happens when we actually get the numbers. When we calculated the numbers of how well they were able to classify, convolutional neural networks were the ones that produced the better results. We also tested, we have a baseline test. In the case that we just went ahead, got the raw data, put it into the out of the box deep learning model, and see how they perform. Baseline values, right? So that's the one that is called no pre-processed. This is our baseline. Then we just pick a popular one. In this case was PCA, principal component analysis, to get some kind of, to try to mitigate the noise that it was in the data, right? And see if they improve or not. And it actually did. When we added this step of adding PCA, the results were better. So we were happy with that, but we wanted to achieve even better results. So that's when we added and started working on our context-based feature augmentation. And when we did that, we actually achieved the best results. This was published already in a journal paper. So that's one of the publications that supports my thesis. Now, on the other side, we have the values from time series prediction. Now, in this case, we're dealing with a different problem, not classification, but prediction. We're trying to predict the future, right? So the idea is the graph should be exactly the same. This yellow and blue lines, they should overlap perfectly. And the next slide is the absolute error. It should be just a straight line on the 0, nothing. As you can see, the values are actually small. It's 0.01, not very big values. But again, these values are also not big. So this is a significant error, I believe. But we went ahead, established a baseline again, and got the results. This is not accuracy, right? And on the table that we have on that I explained previously, the values should get 100. The perfect value is going to be 100 plus minus 0. That's perfect. On this side, you want to have 0 plus minus 0. That would be the perfect thing on this table. Because this one is on terms of the root square error, and this one is in terms of accuracy. So here accuracy is, I think I should replace this word with, let me do that, means root. Yeah. I think that's how it's spelled, right? So you can see that in this case, we focus only on LSTM-based models. Why do we focus only on LSTM models? Because LSTM models take into account historical values, right? The ability of having that short memory really helps the model. We tested different ones. We actually tested convolution-based. We tested LNP, but they didn't work. So when we saw that they were very bad, we tried to focus only on the LSTM models, right? That's when we start looking only on LSTM. That's why you can see that they're all some kind of variant of LSTM. Again, we established a baseline. That's the first road. Then we established a popular that was very successful. that actually it took me the longest time to be actually better than that one. That had very good results. As you can see, it's 0.06 compared to the other ones, almost went half, right? In almost all the cases, almost half the performance was better. The error was reduced by 50%. That's a lot of improvement when using this variation or mode decomposition technique. Very good technique. I was very impressed with it. I was having a very hard time figuring out how to outperform them. But taking into consideration what they were doing, trying to split the signal into modes, right? I went ahead and started thinking that maybe if I add a filter, it would actually also improve it. Maybe we can emphasize differences. And that's when we start looking into this scar filtering, adaptive filtering. Once we optimize it, we achieved these results, which was actually better than all the other ones. Right? We were very happy with the results. I did, again, many runs, multiple runs, cross-validation to make sure that it was not just a lucky thing. And once we collected enough data, we wrote down a manuscript and we submitted for publication, and it's already published. This one was actually published more recently, and I presented it yesterday at the conference down in Orlando. And those are the results that we have so far, right? In the future, we want to focus on adding more different variables, like maybe wind. Wind would be a good environmental variable that we might want to explore how it behaves, either how to classify it or how to predict it. We also consider that based on other publications, based on the results that we have, that our models are actually good enough, right, to perform classification and prediction on environmental data. In terms of computational cost, we did evaluate it, right? But the best models were never the most efficient in terms of that. So there's still a little bit of room to work on how to make it more efficient so we can achieve real-time prediction and real-time classification. So those would be the future lines of research. This and some other projects being supported in part by NSF, DOD, and USGS, and also by the University of the District of Columbia. Right? Here I just cited the two latest, most important ones that where we have most of these results published. Thank you, and now I will take any questions.
Yeah, thank you, Juan. I will start immediately with the questions. Dr. Rosasania, you are having raised hand, and also Dr. Gilma. So Dr. Rosasania, you're the first one. Go ahead. Unmute, please unmute.
Yeah, very good. Can you scroll up a little bit back to the table of your, the last table that you showed to us? Yeah, okay.
Sorry.
So will I be correct or right in assuming that your original contribution here now to this project under the hyperspectral classification is the CFA model? That's your original contribution.
Yes, correct. That's the original contribution.
And on the time series prediction, your original contribution is the one we filter, SAF.
Yes. Correct.
So for your PhD, those two models are the original contribution that you worked on. Yes?
Correct.
So the PCA and VMD, the existing method, they're all existing
Yes, the
method?
PCA is existing method. VMD is an existing method. Yes.
Yeah. What application area were those PCA and VMD applied to?
What do you mean? What application?
Before your environmental application that you're doing here, where were they being used, the PCA and the VMD? What data, what kind of data were they working on?
All kind of data. PCA is very popular, right? Principal component analysis. That's a very popular dimensionality reduction method. So that's being applied in all kind of data. VMD, on the other hand, actually I found it in time series prediction. Uh, so that's why I compared it against it, because it was very
Yeah.
related to what I was doing. When I was looking into what other people were doing, that was the one that we had the latest, like the state of the art values for their specific. I think they were doing. I forgot exactly. I will have to go back to my papers, but DMV in the area with the data set that they were using, they actually achieved a better result. I think in their case, they were trying to target specific things, right? Like rare events, or they were trying to predict
Yeah.
sequence to sequence, right? It was a little bit not exactly what I wanted to do, what we were trying to achieve in our project, but it was very similar. That's why I picked that one.
Yeah.
Because
And
the data.
yeah, in interest of time, we can continue this discussion offline, but in interest of time, Dr. Girma, and after that, Dr. Behera, they have questions. So we take two more questions to follow the schedule. So Dr. Girma, what is your question? You raise your hand. So are you there?
Can you hear
If
me now?
not,
I'm sorry, I think I muted myself. Can you hear me now?
okay, yeah, I can hear right now. Yes.
Okay. My question is, and in your prediction analysis here, were there any theory of information behind that you applied here, uh, behind your data analysis there? When you just go ahead and manipulate it, like for example, entropy or whatever, you can have any other theory of information behind in order to support the research here. That's number one. Number two is that can you tell us, what is the size of your data and during this uh, prediction and classification accuracy there? Thank you.
Yes. So on the first one, I think no. The answer would be no. We didn't use any other metric. That's also part of the future work. Add more metrics to validate the results, right? And the second question was about the size, right? So I think I did include that in the poster. Not super big sizes. They were not big data, if that's the question. But when it comes to the hyperspectra image, the image only has 610 pixels by 340 and 115 channels. These are the spectra different images that we take. So in this case, this is the size of one cube, right? And for the time series, the size of one time series is the data from March to December 1930 to December 21st. Actually, they have up-to-date data. If I go right now to the website, I can download maybe October for sure, 2022. But as when I did this research, I pulled the data, it was December 21st. So and it's monthly, right? This is monthly, so I have one value per month. I have three values per month, average, highest, and I also have all those years, right? Almost 90 years of that, so about 1,000 values.
Okay.
That's the
Thank you.
size of the data.
Thank you. Just to give a kind of recommendation here, I think it would have been your prediction will be even more higher. Had you applied some theory of information behind, taking into consideration, there might be some unknown factor behind in order to determine whether the data is right or not. I mean, the classification, the data classification is coming from one or the other side. Those are the key elements there. And other than that, it's good work. Thank you.
Okay. Dr.
Thank you.
Behera? Yeah. Okay. Thank you. Dr. Behera?
Yes, can you hear me?
Yes, I
Yes.
can hear you. Go
Okay.
ahead.
It is nice to see Ramirez at this stage. Congratulations, Ramirez. Just I didn't get a chance to attend your presentations because I was in another meeting. My question is this: as a computer science scientist, okay, where your contribution will be theoretical side or application side?
Well, I think it's more a little bit of both. I think it has a lot of application on one hand. I did apply a lot of deep learning techniques, coded everything, coded the test bench to run all the experiments, coded every single experiment myself, right? The data load, the data pre-processing, the actual model feeding, the prediction, classification, results, analysis, all of that was done, like coded, right, in a way related to application of computer science. Now, in the theoretical part, there's not pure, I think it's more application then, because I really didn't think about that question before.
So when you present to general audience, the natural questions will come, in your field. If this work is dedicated to computer science, data science, and deep learning, so you have to do that where it is rightly appropriate its space, okay, in the research contribution. That space, identify that space, plus then you have to tell that using this new method, one can apply to many other fields, such as what you gave, stream flow time series analysis, right? So that you make sure that you clear it, because it's a doctoral work. So it's a good idea to make sure that even if your publications, but we have research space all over the place. So you come from computer science background, you see, as you get into your data science, it will be used in data science to if it is so you just break down the fields, so where you stand. Okay, that's my just general comment.
Okay, thank you very much.
Thank you, Dr.
And,
Bahram.
interest of time, we have to move to the next presenter, Temeciu Zewidi. The floor is yours, so go ahead with your presentation. You can share your screen. I think Juan, stop sharing your screen. And right now, Temeciu, it's your turn.
Okay.
To share the screen. Yeah, it's coming.
It's coming.
Yeah, I can see. You can zoom a little bit higher. Yes, much
Okay.
more even. Yeah.
Is it okay?
A little bit bigger, maybe. I can
Okay.
see, but
Let me make it a little bit bigger.
yeah. And also you can put slide by slide.
I will.
Yeah, it is a button. You can see there.
Oh no. Is it okay?
Yeah, for me, it's okay. Yeah.
Is it okay? Can you see Dr. Kote?
Yeah, I can see it. Yeah.
Excellent.
Yeah.
So
Can you make it a little bit bigger? Just like Dr. Kote say, can you show just one slide at a time? The other
Yeah,
one is just...
I will. Give me a minute. Just give me a minute.
Yeah. And Juan, please mute yourself. Okay.
How about now? Is it okay?
No, and the slideshow. Yeah.
Slideshow. Let me run it. Slideshow.
No. Don't go back to slideshow. Okay, that's fine.
No, it's okay. It's nice.
Yes.
Okay, go ahead.
Good afternoon, everyone. Thank you for your coming. My research entitled with the detection of ransomware attack on IoT device deployed on the cloud computing environment using AI machine learning. My advisor is Dr. Grima. He's already in the podium. My presentation will follow the following structure: the introduction, the motivation of the research, problem of the statement, literature reviewed, to looking for something a gap, what is the research question, what hypothesis I will follow, and then at the end of the day, what is the objective of the research to be addressed, what methodology I used, and the result on the experiment, and then the conclusion in the future work. Finally, I will show you the remaining the publication I did so far. As you know, Internet of Things nowadays it is in high peak, and the issue in rotate around the Internet of Things is in high peak. Not only in high peak, but also it have an issue behind the scene, because there is an information transfer in between machine to machine, machine to the person, machine to the computer. So that impacts our world, and then even the volume of the Internet of Things already, as you have seen here, since 2020 and then up to now into 2025, it goes to radically in 15 billions project capital, but 10 years before it was 1 million something, but nowadays it's 15 billions. And then this prediction is exponentially increased. The increase of this IoT, it impacts of the security of a data, especially in terms of the interoperability, in terms of connectivity, in terms of integration of system to system, and also in the architecture side, IoT devices with their huge in number, and then the rules and regulation behind the IoT has also an architectural problem. Because of that, it propagates an issue and then creates a security gap. And the security gap is a cyber attack is also an issue rotated around with this IoT, because the volume is high. All those security issue is already there. Among all those security issues, the malware issue is a significant one. Precisely, ransomware attack is high peak. Research will focus among all those cyber threats in malware, precisely in ransomware. Ransomware nowadays, every news, when you open any radio, TV, and companies has a big peak and a big issue, and then still it is not even get an unaddressed at this moment. So this research by itself, it's in high peak. As you know, ransomware attack is a malicious software which restricts your computer until you paid the ransom, and then unless otherwise, there might not be even the ransoms might not be unlocked. Your data might not be also even after paying. You might not be even get the full data. As you have seen the graph below, how the growth of the ransomware attack from even 2010 years before, it was 325,000 posts. Nowadays, it is 265 million it costs us. And then companies, they tried even to get an insurance even to cover their costs, but still this appetite, this money, it creates some lucrative for the hackers, for ransoms, even to join and then hack industries. So we people as an academia have to have in a big appetite even to address for the problem. So that's why I'm coming and then trying even to do this research. As you have seen, the type of ransomware attacks, the RPD and the email phishing software vulnerability are the big ones. And then this is the growth among across the last year. The motivation of what is the motivation of this research? The motivation of this research is the growth of IoT security threat and the damaging costs of ransom. It motivated me even to detect this ransom, because the cost is 265 billion cost in nowadays, and then all the companies and every issue it propagates to the people. And if something is happening, if the hospital system is hacked with ransomed, and then you can see and then the problem. And this is a big appetite for me. And also the design to address the ransom attack detection model, also to contribute something for the research community, to contribute something for the global security. It is a big appetite for me even to hash and then do these things. And the third one is nowadays is the contemporary ransomware detection has a limitation, because when you review different researchers, they tried even to address some issue with their some sort of accuracy problem, performance problem, or something, an error problem. They tried even to contribute something, but my research based on those state of the art, I tried even to improve that result and getting back to the better detection, ransomware detection application. The problem statement is this research aims to design a new AI model that helps to better to classify and detect IoT-based ransom attack in a cloud computing environment, and to find a solution to ensure the detection of ransomware attack on IoT device. And finally, this research also undertakes security analysis, classification, and detection of the state of the art of the different researchers, and then for especially on the a ransomware attack on a cloud computing environment, and then in precisely with AI machine learning. What are the state of the art? What's research is already so far done in this domain? As you have seen here, the November and then Sabrin already tried even to do something ransomware detection with semi-supervised data, and then they present in 2010 on the international conference, and then they propose AI machine learning algorithm to detect ransomware attack, but their accuracy was, it is an 85% accuracy to detect the ransom with semi-supervised data. And then also they use 90% of their data was the labeled one, which means almost they know which one is, they know predefined information they have it. So the more the labeled data you use, the less the security, the less the result, and then the appetite might have it. And then they have a gap on their research. Their gap is their research. They used in two methodologies, and one's ransomware attack, and then the Bayesian. And then the ransom they detect on 19%, but the Bayesian with 76%. This is a small detection. This is a small accuracy. So I have to. I already have an appetite to see, and then I have to improve this result and gain something better, and then by using a high peak or a high volume of data. The second research already, the state of the art is Ramesh and Agile already they used, they already contribute an automatic dynamic approach of detecting ransomware attack in 2020. They have a default type of computer science solution for their research. This research already is an application based, and then they try even to resolve it, but they have a false prediction, high false prediction on the research. So even if their contribution is a finite state of machine model, and then they tried even to detect for some polymorphic trait of ransomware, but they have also a false prediction on their methods. Ganta and Harris already, and Kumar, they already contribute another research, which is especially ransomware detection in executable file using AI machine learning. So they already present this in 2020, and their contribution is they used 4 methods, and then the decision tree, logistic regression, and then Canyon. Based on their finding, they contribute their maximum result to the 97% accuracy, and that 97% accuracy at that moment, it is, for me, it needs something work, and then to make it better, and then that was not a perfect result, and their validation and the performance evaluation was not demonstrated on the research, but I need to improve this result and getting a better result with high data set with better approach. So the research question, which already I propose, is to answer what the better way to detect a ransomware attack, IoT-based ransomware attack using AI machine learning in a cloud computing environment. What the second one is, how can AI machine learning solution to be better to classify and detect ransomware attack in a cloud computing environment? These are the two research questions which I should be at the end of the research should be addressed. To address this issue, I follow this hypothesis by devising different detection model, as a solution approach using AI model to classify and detect ransomware attack, ransomware cyber threat in a cloud computing environment. The other hypothesis is various AI models such as random ransomware, K-NERST algorithm, neural network, autoencoder, and then the hybrid of autoencoder, nearest KNN, and then autoencoder in random forest algorithm. But checking all these methods and then getting get the best result to address my research questions. The objective of this research is, as I have said, on the motivation and on the problem of the statement, to design a new AI model that helps to better to classify and detect IoT-based ransomware attack on a cloud computing, to find out a solution to the detection, to undertake a security analysis and classification of detection in IoT ransomware attack on cloud computing. These are the objective for this research. So as a methodology, I used especially as a resource to apply a Jupyter Notebook, the AWS EC2 instance, and also Google Colab, especially it's a pro version. On the when I using this, especially the AWS EC2, I used SSH, the command which is a remote server from the local machine to tunnel to access the Jupyter notebook, and then Ember dataset, Ember library file, NumPy, Pandas, Autark, Sklearn, Seburn, and then also MATLAB are used as a library file then to execute. To check, to address, or to answer all my questions, any research is different from another research because of based on the data set which they have. The data set you used it matters, or to determine your result has a high peak or not. I used a data set from Sophos antivirus lab. This research, this Ember data set that has been found from Sophos antivirus, which is a registered trademark of Sophos Limited Company. Sophos Reversing Lab has 20 million data sets, especially on the S4 S3 bucket. This is a public data, no credential are required. The data set contain a feature extracted. For me, 1.1 million data set, I used it, and then you can get this data from this repository server. So to handle this concept, I collect the data set and analyze the previous attack pattern and completely automate the process, and then predictive analysis and prevent the future attack. Classify the prediction process. I already collect the data sets from the Sophos server. So I pre-process avoiding the redundancy, removal of the outlier, and tokenizing the data, and then feature extraction resumed. And once the feature extracted, I use different, as I already proposed in my hypothesis. I use different methods, especially random forest. By the way, my research has a preliminary assessment. My preliminary assessment is based on the first group of methods: random forest, SVM, CNN, the hybrid of CNN, random forest, the hybrid of CNN, SVM, the hybrid of SVM with random forest, and on the triple breed of CNN, random forest, and SVM. I already, my prerequisite, my pre-feasible research already done by that one. And then based on that result, I already taken the high peak result from this, and then adding a new approach, a new methods on top of the one which I have it, and then resume my final research with random forest scanning and neural network, and then the hybrid of autoencoder random forest and autoencoder of Kenyan. Finally, I can predict the ransomware, whether the data is ransomware, and a Bayesian prediction. This is the way all the research is going on. The pre-processing, you know what it is, and then the pre-processing, cleaning the data, and then vectorizing the data, because the data is so huge, so I have to use vectorization. So because of that, I prefer the data vectorization. The data normalization just have to scale up in between because behind the low peak. So that normalization mandatory to make it have and align homogeneous data I need to compute the data. The feature standardization, because all those features should be from 0 to 1, between the standard deviation and between the data, it should be the mean features to be 0 and the standard deviation to be 1. So vectorization, as I have said before, based on the NumPy library file, I use the vectorization. This vectorization, it helps me even the data set to be loaded in the memory, because this is high big data, it's a big data. So to manage this, I use the vectorization. So after the vectorization, then the data layout. The data layout should be labeled. So I have a hash because it's SHA-250 hash of the original file I have. That is a unique identifier for the data feature I have. And the data which I collected from the repository, it is a timestamped data. So, and then the label is 3 levels which I have: the benign, the malicious, and the unlabeled one. All are the 3 of the data divided in 3 equal portions. Then the data labeling, -1 is the unlabeled, 0 is an attack, 1 is a benign. Therefore, if it's the same across the project. So the feature extraction has been done, and this is a high-level architecture of how my ransomware detection looks like. So I captured the data, all the information captured from the IoT data set, already we have it, and that raw data labeled and put it on the repository, and then I trained the data, and using this models can predict either the ransomware attack or the benign file. So this is the way how my model it works. In a preliminary research, I use these methods: ransomware, SVM, CNN. Last time already in the proposal defense, I already presented this result. Based on this result, and then I took it the high peak from this from this research. I took one of the high peak results from there, and then because I dropped the low peak because the competent research, which is the state of the art of the research, the result doesn't even competent enough from the rest of the method. So I already taken from here the high peak, and then by keeping the high peak and then adding a new approach, a new models, Kenyan and the neural network, and then autoencoder, the hybrid of autoencoder with random forest and the autoencoder of the Kenyan, and then I finalized my research with these methods. So why ransomware? Why Kenyan? You know that as you seen here, random forest I already told you, I get already high peak from those pre-assessment results. So I already taken from there. That is one of the big appetite to use this one. And also I can use a few input and then get high result with this ransomware. So as a strategy, I use this ransomware because of these features. The Kenyan is simple even to analyze and required to no training to Kenyan. It is intuitive and simple. And also it's high processing time, especially in Kenyan is homogeneous feature because already my data I tried even to keep them as it is. So I use this one, the contractive autoencoder by minimizing the noise, and then I can even getting the high peak or the high result with this autoencoder. So I prefer this autoencoder because of this benefits, and the autoencoder doesn't even efficient in compared to the generative adversarial network. So that's why even if to use the autoencoder benefit, it have a drawback, but for the benefit of its advantage, I use it autoencoder. And then the neural network, as you know, the neural network, it works entirely, all the entire network, and the only issue is in the knowledge behind the scenes. So I have a precise data, which is 1 million data. So because of that, I can teach or train my data and then get a better result. So the SVM already I use this on the pre-assessment, and then because of its feature, because especially for the supervised data. And CNN I used it, but the result was not promising, and including the entropy to identify the unknown. And I evaluate all my results with the performance evaluation key techniques, especially the precision recall, the F1 square, and the specificity of the data. And by assuring or validating all my results with this performance evaluation metrics, I propose my results. So based on this methodology, this preliminary data set, based on the methodology, I started to present for you the preliminary result. Just let me remind you what it was so far I did before in the preliminary data set. The preliminary data set I used, it was 4,000 data set. Out of that 4,000, 300,000 of them are for training and 100,000 are for testing data. So I tried even to divide all those training data, 100 unlabeled, 100 benign, 100 as an attack. And then for the test set, I used 50,000 for the test set. I use it for the benign and for 50,000 for the attack. So I trained that data, and then by doing that, I get this comparison accuracy result. So among this result, you can see that random forest already has a high peak. It is a 91% accuracy. I get it from there. When I compare this 91% to versus to the literature, the state of the art of the research, which already provided for you as a reference there, it is a little bit lower. So I have to work hard even to get much more better, even from the state of the art, which I have already proposed both for you, because 91% maybe from some of the research might be good. For the remaining 97%, it is far from there. So I will keep it and then doing something additional way of doing to get better, but and the remaining are almost all are down, so I've not even take them and then work on that. So by keeping the random forest from here, because out of 19%, I need to achieve even more from here. So even I was not even consider random for the hybrid approach of random forest with SVM, because my expectation is to proximity to 100. So I'm not even looking for and doing something on the hybrid. So I have to think something different model, because this is research. So I'm not keeping and stacking there. So I add by adding instead of 400,000 data, I use the whole data, 1,100,000 data set, because already I have it. So among this 1,100,000 data set, I use 200,000 of them for the test set, and the remaining 900,000 data set for the test set. And then there are also 1,100 features in it. So I precisely use all the whole data set and then to get in order to get a high result. This is one cause to increase, a big change to differ from this result, which already this result from 400,000 data set, and then as it is I used it and then run it. Because of that I get this result. The algorithm which I used behind the scene was not even include some sort of additional features which I used in the final, but on this one, I already classified the features. This is how the data looks like, the distribution. 300 of them are the benign, 300 of them are the attacks, 300 of them are unlabeled data. This unlabeled data, it gives us even to map our application to know and understand the ambiguity or the noise, and then get a typing. If it is in a 0-day attack, it have a big appetite and then have an ability even to know it. But that was not an issue at this moment. But we put the 300,000 even unlabeled data in it for training, and then finally with 100,000 tests, 200,000 tests for the 100 of them for the benign, 100,000 for the attack. I used it, but additionally I used the twinning algorithm, which is called the hyperparameter, and then the grid search to optimize and get a better accuracy. Previously, I was not even incorporated to get in the pre-assessment based on the recommendation, which we have it in the proposal state, and then adding a new twinning algorithm, I will get I already start to do with this. By considering these two things, I will get a better result in the final. So I did that, and then based on the new models which I already prefer, by taking the random forest and then using additional new models, KNN, autoencoders of random for the hybrid of the two in the neural networks, I got this new result. This new result is a promising result. This new result is achieved more than even from the proposed research we already have it. So 98% of accuracy I get is with random forest. On KNN is 96%. Still, this one is in a high peak when compared to the other researches for the state of the art of the previous research. So the hybrid result, both of them, they have in a 95%, and in neural networks, 96% accuracy they have here. Is it this result? I checked on those metrics, especially the performance perspective. You can see how the performance looks like. So the precision, the recall, the F1 score, and then the accuracy, you can see across the board how it looks like. You can see them. So the random forest already in high peak in all sectors. So all the data which I've seen in here, you can know that the precision and the accuracy and also the F1 score, it tells you it is more than 94%, more than 95% we achieved. So this is a big tech and a big achievement for my research. And so to precisely see how it looks like, how all this from so the combination of this result in performance perspective, you can see that how the true positive looks like. Almost we do have 200,000 test set. You can see that almost 98,126 are the true positive, 96,300 are the false positive. So you can see that when you add both of them, it is 98% of it is achieved, and then this 1874, and then why is it one the right area? You can take them, it is insignificant when you compare to the other research. So from the accuracy perspective, our research is happy. It is not necessarily a problem that depends on heavily on what the final must be to do. So the better the accuracy is, the better the result to have it. The second one,
Yeah.
you can see it from here.
So Demetrio,
Yes.
we have 5 minutes. So
Okay.
you have to keep the time. Yeah, 5 minutes and try to get the conclusions. Yeah.
I'm almost done.
Okay, good.
As you have seen here on the area under the curve, you can see from here, this graph, it tells you the area covers with the 4 of the meters, which I use them, you can see them, all are orderable from the corner. The random forest almost, it is approached to 1, which means that the higher the area under the cover you have, your performance model distinguish the positive and the negative class perfectly. If it is 1, means it is precisely 100% that race. Random forest 98% is without any hesitation. We can take it. The remaining, you can see that the KNN 98%. The hybrid of the AE, the autoencoder random forest is 99%, which means that the classifier can perfectly distinguish the positive is positive, the negative is negative, which is correctly classified the result. So when I compare my result versus to the state of the art, which I have it already proposed, my result is the right side, and the comparator result is here. The ransomware detection against semi-supervised research, which is the first research, they got rapid random forest, they got 19% accuracy. My accuracy is 98%, is a better result. On the second research, they use the framework of the analyzing ransomware using machine learning. They used 2 methods, the Bayesian and the random forest. They got 76 and 90%. My result, as you have seen here, 96, 98, 96, 96, and 95. All my result is even beyond the state of the art of the research. On the third research, which already on the executable, they got 97. On the logistic rigor, they get 97. Also, the decision tree 78. The k-nearest is 95. My result is 98. It's still better. The neural network 96. They were not even used it. And the decision tree is there 78. I was not used it. Even the KNN, their result is 95. Mine is 96. It is still better. So I can conclude that based on the comments which I received from proposal, my defense and our research assessment result, we have narrowed down our approach to get a maximum result. I did it using the more data set and hyper parameter, and grid search helped me even to find the best performance associated with the model. Of course, yes, I did it, and you have seen it already. Based on the new AI models that are better to the classify in the IoT-based ransomware attack, already we achieved it based on the approach. Finally, we find out a solution to ensure the detection of ransomware on IoT deployed cloud computing environment to secure data. And then this research examined various models and algorithms, security analysis, classification to detect IoT and based on IoT-based ransomware attack in a cloud computing environment. So, but this result is not 100%. So I don't have a future work. In this research, why we use a static data set. So if this study expands to non-static data, real-time data, if the program is retrieved and analyzed in real-time scenario, we may get different results. So if we use this research with the real-time data, maybe the result differ. On the other hand, the data set I used is limited to the number of ransomware variants, since I used my data in 2017, 2018 collected data set from Sophos research. Therefore, the updated version of the dataset may include all the ransomware variants, because for the last 3 years, number of new variants ransomware are created. My research dataset is not included all those new ones. So the result, if I included all those in the future, more lucrative data will come, result will be coming. So I already published some of my research. This one is a recent publication. I have 6 publications. Ransomware attack detection on Internet of Things. Already this one is published. Secure software defined network. Already this one is published. Evaluation of network machine learning model on DDoS attack and intrusion target. Already this one is published. All these are on IEEE. And the malware detection is already published, and then the IoT security and role of machine learning, this is published, usable security and case of remote web. All these are the 6 papers are published, presented in international conference, 3 different international conference. This is what I have so far. Thank you very much. If you have any question, you are so welcome.
So the floor is open for discussion. I have just one comment. I'm familiar with your work because you were supported from ARIS grant, and I would like to mention that support your thesis, because it's very important to recognize the federal funding, which helped us to get some results. So from audience, if there are other questions, comments, observations.
I think, even if it's not fair to say anything for me, but as a part of research, you need to avoid saying ransomware. And you know, the word ransomware is already in your mouth, and you repeat it instead of saying random forest, you're saying ransomware. So you need to improve that. You know, when you make your final dissertation defense on the 13th of December, you need to be careful on those kind of things. And there are some small hicks that I'm going to let you know at the later stage. So far, that's it. It's better to listen from the others.
Thank you very much. Thank you.
I got a couple of questions.
Yeah, go ahead, Dr. Shahiria.
First of all, thank you so much for the presentation. I have a few questions. The first one is regarding your training time. How much time did you spend, or your algorithm for each training takes?
Can I answer now or?
Yeah, it's about timing first. How much that is important for you?
Yeah, especially on the pre-feasible training, one of the especially the ransomware with the random forest, it takes almost 31 hours to get a result. I use the AWS environment, and then that is a high peak and high GPU, and then when I tested it takes even to get the result, because the volume of the data is too high. So by minimizing the data, I get a better result with a minimum time. The others, a little bit, half an a day, some of them, and the others also get something 1 hour, something like that. So the totally, for the last 2 years, I already working with this, and then nowadays I get with this result. The more you use it, the high GPU, the less the time you use. So what I'm learning from this research is from where you get the high GPU environment. And then the recent one I use with I subscribe the Google Colab with a pro version, and then I subscribe from them, and then I use the high GPU data, and then I get a small time when I run all those entire data sets. So this is what I have.
Okay, so I got not, my question has not been answered. What was the time for actually for training, the running time for your algorithms, different algorithms? You said 31 hours?
Yeah, when the first time when I I have almost 7 models which I used, as you have in the pre-assessment, and then when I independently train all those data, the training result, it takes a while, and then sometimes when the time is up, I feel as if I'm doing wrong, but when I check them with the systems, it's okay, this is the right way it works, and then at the end of the day I get, after 31 hours, 1 day and 8 hours, I get the result. Because it's the system says wait, and then after 31 hours, I get the result. This was I was done a year before. So based on this, I improved the algorithms, I improved the way I already select the features, and then get a less time with a high GPU with in order to get the result. So I improved by adding the methodology. I improved the data set in the future. I improved the way I used and then combine the data and then feed it to the system. And then because of that, I try time to time to minimize it and then get the results easily. So this is what I have. May I answer your question?
My next question is regarding your future work. You mentioned that you're going to have that in the future to run it in the real time. And there is a huge difference between 31 hours and real time. So what would you do that?
Yeah. When I use the huge, these 31 hours, by the way, these 31 hours was when I start to test, when I start this research and to test all the data which I have. That's why from local machine to the AWS environment, I already obliged to be there to get high memory to execute the data. When we go to the high volume or high GPU machine, this will not be an issue. And when you come to the real environment, this is a testing environment. So I will subscribe a high GPU environment, and then I will put it all my applications there. If the traffic is coming in the real time, automatically, depending upon the investment which I have, I can execute easily, because when I use my Google Pro on the last or the final execution, it's not even take even more than even an hour. So which means that the limitation is the payment which I paid for the machine. So when it's in real time, your environment, it matters. And then your environment means the machine you use, it matters. So when you have a high spec machine, definitely that will not be an issue. Automatically the application worker then slash and then get you a solution there. So this is what I have.
Can I say something, Dr. Amir, here, just to put in perspective what Mitch was saying? When you say the real time, the main issue while we do this research was the availability of resources. There was a huge personal expense from AWS then, because I was pushy a little bit, and of course he has to do it. We need to get some result, and I just pushed to the limit. Then we just moved to Google. Then the resource that we get there after a certain subscription was very, very, very dramatically changed. And there are also others, other resources, but as you know, there is no any support. Thanks to Iris, we had some financial support there, but other than that, there was some limitation. But with those limitations, that was what he was talking about. Provided that, I think he should, like you said, he should mention on that future work statement that provided that the availability of resources they are enhanced, then he can go ahead and the research can be extended to the next level. I think in real time in 31 hours, of course there is a huge difference, but from that 31 hours it has already been all the way down to the minimal, but still there is some gap between the real time and whatever he was talking about during his research time. But I feel with this such an availability of a higher level of resources, it's expected, of course it's a huge research work, but it is expected to have a more better result.
I see. I noticed that most of the time, almost all of the time, your results, they're kind of biased on the random forest, and you got the better results on the random forest. So my question, get back to the data that you've been using. So I think that the class of data or the data size that you used were too huge, and comparing that was kind of very, very, of course, dependent to the data. My next question is regarding if you reduce the data size or data bank that you already use, then what would you get? What do you expect to get? Because not always you are going to have the data available that much size, especially then even for the future, if you focus on, reducing the time, of course, the data availability of the data is kind of a limitation for you. What if your data size is not that, complete, or let's say that huge? Have you tried the lower data size, not that big?
Did you see this graph? Can you see this comparison? This is the pre-assessment result. The data sets which are used is 1/3 of the 1,100,000 data sets.
100,000 is a huge data set.
No, for this one, I use.
Go back to your.
This is 400,000 data set. 300 of them the training set. 100,000 of them are the test set. I used 400,000 only for this result,
Okay,
but
so
its
I'm talking
accuracy
about
is less.
way less than 100,000. Because in one of your slides, you brought the results, compared the Bayesian network, which you got 76%, and of course, random forest, 97%. Yeah, here it is. So 90%, 76%. But this comparison is not accurate. If you reduce the data size, definitely Bayesian network is going to dominate the other, of course, methodologies. That's pretty much good for the lower data set. And if you come up with this conclusion, you have to mention the data set is huge. Otherwise, you have to study and reduce your data set size, and of course, again, redo that and see the Bayesian network and the domination of that network, that methodology. And this is only good for the data set you used already. And the other question is that, did you use exact same data that you provided here in reference 17 and compared your methodologies with that? And
No.
then how could you say that your methodology is better than the other papers? If you have not used the same data set, you cannot provide that statement. Unless you have exact same data set, and then you can compare the methodologies. Otherwise, this is not a correct statement you're talking about.
I think let me correct him here. I think it is better to say here that you need to put here, for example, for the 76th percentile of the accuracy result with the other people's work there. It's better to put at least the size of the data that they use, so that it will be easier for the audience to see, okay, this is the amount of data that's been used, applied by the researcher A, and your approach there, so that it can give a sense from the type, the set of data. The data might be the same, the nature of the data is different, but the nature of the data is the same, but the type of the data might be different. So that's the key.
The comparison is not accurate. If exact same data you use, then you can compare them. Otherwise, this is not a correct comparison. I think you have to be careful about that, and you have to revise that.
Can I answer some questions here?
Yeah, definitely.
Let me tell you something. Whatsoever it is, this is ransomware attack. The ransomware, the characteristics of the ransomware, in any case, it is almost identical. It's almost identical. Whether you use a Bayesian, it's a method.
What do you mean by almost identical? I don't understand.
Almost identical. There are a number of variants of ransomware attacks. There is a number of variants of ransomware attack. Their property almost the same. Different researchers prove that the deviation between the variant is not as such significantly differ. Whether you use something Robux or something MyLab or something, a different ransomware attack inside in it, all those properties inherit the same type of something ransomware feature. So whether they use something different, I know the Bayesian and this research they use 5,600 data sets for their framework, for their data set. It is a small data already. They explained it, and then we used the small data set, which is 5,600 something. Already they used it that one. I don't need even to use that 5,600. Even my earliest project, I have already used the same methodology, and then I get 100% accuracy result with a small data set. But I don't need even to take it and put it here and then to make a big high, because the representation, when you use the high representation on your data set, you broadly address a number of variants you have. My data set include all, at least the maximum number of variant in it, and then it is more representative than precisely with some sort of 5 or 6 something and then small data set and getting high because that's not as such a result. So I tried, but to make them beat and then try to use their result and pick my data, maybe it gives a sense. For me, I'm not saying anything. The characteristics of any attack, especially from malware perspective, among the malware, what is the difference and what is the thing behind the malwares? That is the key issue. Whether, because all they are saying analyzing ransomware, attack ransomware, a ransomware. When they are saying ransomware, we are talking about on the same area of research, on the same variants. So the methodology we used to detect all those ransomware, it matters. Mine is better. Still, I'm keeping with high representation of data, high representation I have, because I used high volume of data to address all the type of ransomwares. But those who are not included for the last 3 years, of course, I put it as an open for future work. So this is what I have so far.
Okay, so in interest of time, I encourage you to continue this conversation offline, which is a very interesting conversation, should be addressed, because we are way above our presentation. So the next presenter is Vincent, and he will present his achievement in research. Vincent, please unmute. And Demetrio, please stop your sharing. Okay, very good. So Vincent, are you there?
Yes, I'm here. I'm trying to share my screen, but I don't see.
Yeah, we are a little bit late, but it's a good conversation, very good questions, which should be addressed.
Before Vincent gets started, just want to make sure that, have you published any journal papers on this work?
Yes.
Where did you publish them? How many journal papers did you publish?
6.
No, journal papers, not conference papers.
2.
Where did you publish them?
IACIS.
Okay, thank you.
Okay, let's move on. And the next presenter is Vincent. Vincent, the floor is yours. Go ahead.
Oh, can you see my screen?
Not yet. I have seen before, but not right now.
I don't know what I touched. Hold on. What happened? Stop sharing.
I saw it before. Maybe you have to reconnect again.
I will do it again.
Yeah.
All right.
Yeah, now I can see it. Go ahead.
So, good evening, everyone. I'm Vincent, PhD candidate in the Department of Computer Science and Engineering. And before I tackle the content of the dissertation, I think one of the peers asked a question here about the contribution that, as a computer science a student, we can bring to the table. I'm a data scientist. I work as a data scientist. I think one of the major problems that computer science or statistician or economist or other fields are facing is how they can build a model from scratch. So it means that if you have like a bunch of data and one of your supervisor or the project says that develop a model where a prediction can be made. So you have a bunch of data. How do you determine among those data which one you will consider as a dependent variable and which one you will consider as an independent variable? And among those independent variables, which one will be the most independent variable that you should use? So in this dissertation, what we are proposing we first of all we go to the introduction, address the problem, the research questions, the research objective, discuss about the literature review, the data sources, provide the descriptive statistic, the wind speed over in the United States, overview in the United States, discuss the approach and present the result and what are the significance of this study. So basically the main purpose here is to analyze wind speed data, but how do we use wind speed data? Wind speed data is used as a domestic source of energy. The importance here is that wind farm provides wind energy, reduction of the amount of electricity. Now, the growth here, especially in the United States, there's a rapid growth every year regarding the wind speed data. And this information came from the Office of Efficiency Energy of Renewable Energy. So the key problem here is uncertainty. Wind speed can be compared to stock markets. When you have uncertainty in the data, it's difficult, really difficult to predict. But what model can you use to predict those data? The second key problem that we're trying to address here is the impact among the data. So it means that you have many data, but do you know how to analyze any relationship or dependencies among those data? This is one of the questions that we're trying to address. Now, the homogeneous mixture distribution. Air is kind of uniform. It looks uniform. But the problem here is constituted difficult to detect. So they look homogeneous, but it's difficult to detect the content. Now, why here we say that one of the key problem is the model not yet being addressed. We'll describe this one because the model that we use here is a combination of 3 different pipelines to clearly dig to the data, analyze the data, the relationship among the data, the dependency, and then also do the prediction. So the research question here is, when we use the data that we split it in different data sizes, do the coefficient matters or the parameters matters or differ? What to expect when modeling uncertainty using multiple dependent wind farms? Another question here is how to analyze high dependency within the data, especially the wind speed data. Does the data size matter? These are the kind of questions that we're trying to answer here. So the literature review, I earlier mentioned about the multiple data, wind farm data. So the most important thesis that we followed here is the one developed by Dr. Shairina, where he write a probability model of wind penetrated power system, only model a single wind farm in a wind penetrated power system. In that model, we, instead of using like one single wind farm, we're using like multiple wind farms. And I think one of the feature work that Dr. Shairina was trying to address is how to use the Vine coupler to answer this question. Now, the rest of the literature review, they use single method that we have here in our dissertation. They use single method. For example, Dr. Shairifa used like a Bayesian linear regression approach. Dr. Su used a Vine coupler approach. And another one also used like, the Zoo also used a Vine coupler approach. But in our case, this is our research objective here. It means that instead of using like only one approach, we try to combine those 3 approaches before doing the predictions. So first of all, we use the non-Bayesian and Bayesian method for coefficient and parameter estimation. The second one is the Vine coupler application for high dimensional dependency model. The third one is the Bayesian model moving average, to analyze model uncertainty in canonical regression. And then with you, we end up with the prediction. Now, the data sources. We use 15 data variables that we collected from the National Renewable Energy Laboratory. And the software that we use here are RStudio, Python, and Excel. Now, the sample size of the data, we use hourly data, which is like 8,760 observations. The daily data is 365, and the monthly data is 53.
That's
Now, this is the descriptive statistics of all of the data that we use. We use like,
go back. That is not a monthly data. That is a weekly data.
oh, thank you. Sorry. So these are the data that we use, the different type of the wind speed data. You have like, especially the descriptive statistics here only shows like the hourly data. And we can see like the mean for most of the data is pretty much around 6 to 8. And the standard deviation is in average like 3. And then you have the mean and the max here. Now, the wind speed data in the US, we can see that since 2004, there is an exponential growth in terms of the wind generation in the United States since 1990. So from 2004, we can practically see like an exponential growth. Now, the wind electricity generation, this is per hour. So Texas leads those different states with 92.90, and the last one is Nebraska. Now, the wind speed impacts. The advantage here of using like wind speed for different things is like there's a job creation. And it's also a source of revenue for farmers, and it cost effectiveness. There's like a development in terms of infrastructures, tourism. But the disadvantage here is the noise pollution from the turbine, the dependence on weather. Now, the big one that we're trying to address here is the uncertainty. That's why we bold this one here, the uncertainty. These are the approach that we're trying to use. The first one is the non-Bayesian model. The non-Bayesian model is like the regular regression model, the inferential statistical model that we usually use, even econometrics use also, where you have like dependent, and then you have a bunch of, you have a dependent variable and then a bunch of independent variable. So first, on the non-Bayesian model, we use a correlation matrix. I will explain why we use the correlation matrix, followed by the random forest for feature selection. Then, once we do the features, random forest for feature selections, we have our multiple linear regression. Now, there's like a fifth that it's called the imposition of variance inflation factor. I will tell you why we use the fifth here and why it is so important to use the variance inflation factor. Then once you've done this, after using the variance inflation factor, you have the fitted model. So the fitted model here will be the one that we will also test like the KS test, which is a statistical test to see if two samples are coming from the same distributions. And we use the fitted model in the Bayesian model. So the Bayesian model is pretty much based on the probability. So we have a prior belief that we multiply by the likelihood to get a posterior prediction. We also use like a Markov chain Monte Carlo. Markov chain Monte Carlo is kind of similar to the reinforcement learning, where you're learning like for different states and then provide those dependency or prediction. Now, for the dependency, we also use the Vine-Kaplan. Vine-Kaplan is one of the methods for those who like to analyze stock markets. It's one of the methods that we use here to evaluate the dependency among the data. So first of all, you have to transform the data to a Kaplan data. It means that normalize the data. Then you use the Kendall-Toe application. for the correlation methods. You don't use the Pearson, use the Kendall tool application. And then we use the Archimedean and elliptical copula. So the Archimedean and elliptical copula are also different type of copula, where we have like the Frank copula, the Gamble copula, and some of them. So now the AIC, BIC, and log-like loads. So in statistical method, use like the AIC, and the log AIC and BIC can help you select the best model. Now, after that, we evaluate our different vine. We have like R vine. R stands for regular vine. We have like C vine, which is the canonical vine, and D vine, I think, is forget, but I will come back to this one. Now, once we finish this, the last one is the Bayesian moving average. The Bayesian moving average is a method that is specially developed to analyze uncertainty in the canonical regression. So the application here would be used on the daily data, which is 365. Well, we will, based on the result that we obtain, we will see why we use like the daily data. Now we have the posterior inclusion probability, we have the post-mean, the coefficient selection, and the model selection. Now the canonical regression application also will be addressed. Now we will forecast based on the predictive density model. The Bayesian and non-Bayesian, the non-Bayesian and the Bayesian model results that we obtain from our analysis. Remember, I earlier talked about the correlation metrics and the random forest. So if you are a data scientist, your supervisor comes to you and he say, okay, Vincent, we have a lot of data here, but we don't understand how to develop a model from this data. The first thing that you have to do is to write a correlation matrix, assign a cutoff of 0.5. When you design your correlation matrix, the first variable that comes to the top, why I did circle this one, when you average all of the result of the correlation and you compare to the others, the one on the top comes higher. So you use this one as your dependent variable. So this variable is highly correlated with other variables. Once you have your dependent variable, you achieve one step. Now, what about the rest of the data? How do you determine which one has a strong importance or impact on the dependent variable that you select? That's where you do the random forest. When you do the random forest, it comes out that the first variable here is the one on the top because it's like listed in order from the highest to the lowest. You can do from the lowest to the highest, but in this case, I did to the highest to the lowest. So our dependent variable that we picked for the non-Bayesian and Bayesian model is amble. Now, the independent variable that we must keep in our regression analysis is Bear Creek. Now, the non-Bayesian model results. So the first table shows the variation inflation factor. The second table shows the regression result. So let's talk about the variation inflation factor. So when you run a regression model, you have to make sure that your independent variable are not correlated or there is no in existence of multicollinearity among the data. That's where you use the VIF. So the variance inflation factor, when it's equal to 1, you must keep those data. So we run the first regression here that we call Amble 1. So on the first regression model, the R square was 83%, I mean 0.83, which is normal because we have all of the data included here. But when you check the VIF, the variance inflation factor, most of them here are pretty much high. So we proceed by eliminating the high variance variance inflation factor. Now, something that I forget to mention, we started with 15 data variables, but when we use the correlation metrics, we only selected variables that are 0.5 correlated to others. So we decreased the data from 15 to, and here we have like 1, 2, 3, 4, 5, 6, 7, 8, 9 variables instead of 15. That's why you can see those variables here. So we have 8 variables as an independent variable, and then 1 variable as a dependent variable. Now we eliminated all of the value, the variable that have a high variance inflation factor. But remember, we must keep the Bear Creek variable. Why? Because Bear Creek was the one we selected here. That has the most important on Ambor. Now, on the second round of the regression, this is what we have here. 2.32, 2.59, and then we just remove those data. Now, finally, the width here, we have 1, 1. It means that among our independent variable, there is no multicollinearity. There's no dependence between those variables. So you can use those to predict or to analyze your dependent variable. Now, when we use this one, the R squared, of course, decrease because R squared decrease when the data also decrease. Now, we tested the same thing using different size of the data. You see that for the hourly data, where we have 8,760, the coefficient here for Bear Creek was 0.87. We rounded up, it was 0.87. It means that for 1 unit of change of Bear Creek, Ambor also changed by 0.87. But the R square here was 0.78. But when we tested the same thing using the daily data, Bear Creek has strong coefficient, which is 0.95. And the R square here is 0.91. So we can also see that the p-value here is also significant. It's lower than 0.005. On the last one, which is I think I need to, don't know why I keep writing like, should be weekly. It was like 0.86, and the coefficient was 95%. I mean, 0.95. Now, this is the Bayesian model. So the Bayesian model also, surprisingly, the Bayesian model also provides the same coefficient. So earlier, I was mentioning one of the author who also used Bayesian and non-Bayesian and found that Bayesian was like much promising compared to the non-Bayesian. But in our case here, using the wind speed data, both came up with the same result. And this is the Markov chain Monte Carlo that we use. We also get the same result here, 0.86, which is now far to 0.87. Now, when you use like the large, what we call large here is basically the hourly data. What we call medium here is the daily data, and small here is the weekly. The weekly data. So we can see that the posterior, the posterior that we have here, when you use this is the intercept, I think is also lined up around the mean, which is between 0.86 and 0.87, same as the result we got over there, and which is also similar here for the medium size of the data, which is 0.84, same as the one we receive over there. Now, the KS test. So the KS test basically is a statistical test here to see if two samples are coming from the same distribution. We use Bear Creek, we use MPIC utilities. When you see the cumulative density functions here, cumulative distribution here, they're pretty much the same here. And you can see that the D value, which is also when the D is lower than 0.05, it means that those two samples are coming from the same distribution. So basically, this test here confirm the method that we use to detect those dependent and independent variables when we apply the correlation metrics and random forest. Now, Vine-Coupler model. So on the first model that we use, which involved the non-Bayesian and the Bayesian, it was based on the relationship, the correlation metrics. But the dependency is kind of different. We different data. So you will see here that where the data were not normalized, you can see that there is a bunch of outliers. So A here represent the hourly data, and B here represent the normalized hourly data. E here represent the daily data. I mean, C here represent the daily data, you see, also those outliers, and this is the normalized. And finally, this is the weekly data. You see, there's not too much outliers, but some of them has outliers. And this is the normalized one. So this table here, we have some acronym that we use to define the, to design the Vine-Coupler. And these are the edges. So edges means that is like the identity of each emblem. So you can use the edges to define, to draw your, or design your Vine-Coupler, or you can use the acronym. So instead of using the edges, I prefer using the acronym. So when you see like HBL, it means emblem. This is net power. This is Criterion Reed Park. This is Rough Rock. This is Free Farm. This is Bear Creek. This is Mountaineer. And this is Locust Ridge. On the other side, these represent the Archimedean and elliptical coupler. So basically, we have the Frank coupler, the Clayton coupler, and this is how the Frank coupler looks like. And the Clayton coupler is like, the tail is a little bit, here is a little bit wide, but we have like a tail here. This is the Gamble coupler, and it looks straight also. And then you have a student T. Student T basically works for stock markets, to analyze stock market when you use like Vine-Coupler approach. And then we have like the normal, which is the Gaussian coupler. So after transforming the data using like the Kendall toe, this is what you can see here. How the data are correlated or are dependent on each other here. So you can see that net power and Criterion Reed Park shows like a 0.71 correlation here. And what I can see here, you have Criterion Reed Park and Rough Rock, which is 0.85. I'm addressing those variables because they will be important in the future, I mean, in the next slides. Now, when you have like, for the large data set, this is how basically the R vine, the C vine, and the D vine coupler are represented. So basically, we have like 8 variable, correct? Because for the Vine-Coupler, we removed the last one, which was the MTP utility. So we kept like 8 variable because of the Kendall autocorrelation metrics I use here. So basically, when you have 8 variable and then you do the R Vine-Coupler, you are supposed to get 7 trees. It means that the number variable minus 1, you get 7 trees. But the most important trees that you must show here is the first one. The R vine here, this is the R vine. we can see that Humboldt has a strong impact on Bear Creek using the student T, which is 0.7, and but is not directly related to Locust Ridge. But Bear Creek and Locust Ridge shows a Gaussian dependency here, Karpla, which is 0.52. Now, this is the Frey Farm. Frey Farm depends. The dependence of Frey Farm to Humboldt is straight here. This is the first group. Now, on the second side, on the other side, you have net power.
Yeah, Vincent, you have 5 minutes.
Wow.
Yeah, well, I mentioned in the presentation 20 minutes for presentation, 10 minutes for questions. So we have more than.
Okay, that's fine. So let me move forward very quick. So on the large data set, what I wanted to point here, on the large data set, the most dependent, strong variable that all of the others are dependent to is net power. On the medium data set, instead of net power, it's ample. So it means that when the data are reduced, it's ample. But when we have large data sets, it's net power. This is the same observation for the small data set also that we find here. So here's the thing. We have the results. We have the log likelihood. We have like the AIC and the BIC. You see that here when we use like the medium data size here, the AIC and the R-vine and the C-vine gave us the same result for the AIC. And the BIC, the Bayesian also, the Bayesian criterion here, the R-vine and the C-vine gave us the same result. This is one of the reasons that we use the weekly data to predict the data, because the R-vine and the C-vine here give us the same result here. Now, this is the Bayesian that we use. So on the Bayesian, we run 3 different equations. So we use like Bear Creek as a dependent variable because of the strong dependency that Bear Creek has with Humboldt. On the second model, we use like criterion. So on the Bear Creek here, you see that Humboldt has like a strong post mean, which is 0.87. So it means that we use Humboldt to predict Bear Creek. On the second equation, Rough Rock has a strong correlation, a post mean with criterion wing path. Lastly, on the third equation, you can see that net power and Rough Rock is 0.63, the post mean. Now here, the blue result, the blue color means that a positive coefficient. The red one is a negative coefficient. So on the first equation, when you run like a model based on a best 500 model, you can see that Humboldt, of course, that we already showed, has a positive correlation, coefficient with Bear Creek. And the second one is criterion read pack on Rough Rock, and the last one is net power on criterion read pack. Now here, we run different models. We have the uniform, the fixed, and the random. So you can see that here on the first equation, Humboldt also comes first based on what we discovered earlier. On the second equation, you have Rough Rock here. And lastly, you have criterion wind pack here. Now, this is the Monte-Carlo Markov chain for different equations. You can see that the correlation is like almost like 0.90 for the first equation. This is 0.9093 for the second, and this is the third one. And you have the marginal density Humboldt, which is the posterior inclusion probability, which is 100% here for all of these equations. Now, this is the prediction. So the first equation, this is the prediction we have for Bear Creek using Humboldt to predict Bear Creek. This is the second one we have using a Rough Rock to predict criterion wing pack. And this is the Rough Rock using like criterion wing pack here. So the prediction is far away from the real value. Now, this is the accuracy, the prediction accuracy. As I mentioned, predicting data with a nature of uncertainty is, we can say, difficult, sometimes impossible. But what we were able to achieve here is like the criterion we pack shows an accuracy of 0.84. I know it's not close to 90, but with a large of uncertainty among the data, it's difficult to predict. And Bear Creek comes at the second rank with 0.74, and the last one is Rough Rock. So what contribution that we bring into the table? First of all, is to demonstrate that how different methods such as Bayesian, non-Bayesian, and Van Capilla, and Bayesian moving average can be applied to analyze data that deals with the nature of uncertainty. And the second one is provided a statistical and machine learning steps by step orientation for dependent and independent variable selection. And also, I think our work will be like we have like a major contribution on the literature. Now, for the future work, even though I did not mention here, the future work will be to use the co-integration followed by the causality. Thank you.
Thank you very much. So now we have time for questions. So if there are any questions, let's address them right now. I have some suggestions like before. So the first question, how many publications do you have so far?
So far, we have published one paper. We have two more that we submitted. But beside that, I have like other publications in economics and statistics. But related to the computer science, we published, the first publication was based on the Bayesian and non-Bayesian. We have, because we run like two different papers. The first one was the non-Bayesian and Bayesian, where we address the methodology that we can use from building a scratch model, a model from scratch data. The other one is the Van Kaplan, and the last one is the Bayesian moving average that we submitted.
Okay. Any support from the grant?
I think, yes, with NSF, I think I mentioned this on my dissertation. And also, you also see that on this PowerPoint, we didn't include any formulas because everything will be on the dissertation. And Dr. Shairina is my advisor. In place of the grant, I received a lot of support from him.
Okay, you have to mention.
Okay, this is part of the Research Initiation Award. And before Vincent got his industrial job, it was fully supported by the grant, NSF grant.
Okay, very good. Yeah, because I like to be uniform for all the candidates. And after this presentation, I will have discussions based on what I have seen today with the advisor and the student before to move on. So probably tomorrow or after tomorrow, we'll discuss more or verbally when we meet each other. If there are no more questions, we are already late because I allowed for any candidate to present more than 20 minutes and also to allow more questions than 10 minutes. I would like to thank you for all 3 PhD candidates. I would like you to wish the best for your defense, which is scheduled in the middle of December. Before to submit the draft of your PhD thesis, you should get approval from your advisor. So he's the first in line approving that, and make a CC to me and to any member, and we'll move from there. We have 2 weeks in front of us, so we can do many things, finalizing, polishing, and presenting a best draft, which will be published on the UDC repository site. So keep in mind that. And also any other issues will keep you informed about the process and graduation. And please, we'll address that by email or in person when we meet each other. Again, thank you very much. It was the first presentation of 3 PhD candidates for this fall. We'll continue, and in the future, we have more candidates coming and more events like this. Thank you very much, and have a nice evening. Thank you.
Thank you.
Thank you, Dr. Cote. Have a great night. Everybody, thank you.
Okay, everyone. Bye-bye.
Thank you, everyone. Have a good night.
Thank you.